All right, so starting from today, we're going to focus more on algorithm design. In particular, we're going to focus on graph algorithms, different ways to manipulate, to process graphs, okay? Today, what we're going to do is that we're going to introduce graphs and how to represent graphs. But first, some motivation. Why do we care about a graph type of data? Well, if you think about it, in the modern data era, what are the most common type of data that we encounter? Well, one type is basically we're given a set of feature vectors in some feature space. Okay, so basically, say you have a collection of patients' record, and each of the patient is represented by a feature vector. They consisting of information like what's the name, the age, health history, and so on. So you can think that each patient now is represented by some high-dimensional vector. Okay, that can be considered as a vector in d-dimensional space. Okay, so this kind of representation give us rich description of the data we're interested in and focus on the individual attributes. Okay, graphs, on the other hand, focus on what are the relations among individuals. Okay, and we see this graph type of data is very ubiquitous in many applications. We use it all the time with social networks. And in the academic world, there's the co-authorship networks, there are knowledge graphs in the biological medicine literature. There are different biological systems modeled as graphs. In the brain, we study the brain networks and so on. Okay, so by far, the type of feature vectors or the graph data are two most common type of data that we encounter frequently in practice in different applications. Okay, so it's a very important one. Now here are just some examples. For example, the different type of social networks. The first one is basically the social gram of second grade class, where different students interact with different students. Okay, and the right one is the Facebook friendship social graph, where two nodes, each node represent a person, and two nodes are connected if they are Facebook friends. Okay, have that relation. Okay. You can, here's a biological network. This is a so-called protein-protein interaction network, where each of the little dots, the graph nodes, represent some protein molecules. We know that in our body, the main worker inside is small molecules called proteins. Okay, so each of these dots is a specific type of protein, and then there's an edge between them. If two proteins interact, the interaction is essentially how to make our body function. Okay, and this is a more geometric network graph. This is the road network. In this particular case, it's the Tokyo subway map, but you can also imagine that when each time you open the Google map, then you have a geometric graph there to show you how you can go between different stops, different cities, and so on. Okay. All right, so now the graph type of data are abundant, okay? But what is a graph? Well, mathematically, a graph is by G is basically a pair, V and E, where V is called graph nodes. Okay, so like in the social network, those are the people, the nodes represent the person, and E is basically subset of pairs of nodes. These are called edges. Okay, where an edge, basically a pair of nodes A and B, represent either some relation between the pair of graph nodes, or represent, say, the distance between them, and so on. Okay, all right. Now, when we talk about graphs, the graph can be directed or undirected. Okay, so we're going to introduce the concepts separately and then motivate each of them as well. So what is a directed network? A direct graph network, a direct graph is a pair where we have a set of nodes V, and the E is a set of ordered pair. Okay, so there's an ordering between two nodes. Okay, these are called directed edges. So for example, here, the standard representation of graph is the following. We give what is the set of nodes V, what is the set of edges. Okay, so in this particular example, the set of nodes are A, B, C, D, E, F. Okay, and what are set of edges? They are each is a pair of ordered pair of nodes. So if, for example, AB means that there's an edge going from A to B. And this can also be very conveniently represented by drawing it as the graph that we often see. So usually when we talk about graph, we kind of have this visual picture, which is this, okay? But really this is representing the same information as what we see here, okay? So for example, an edge AB means that I have an edge going from A to B. I use this arrow to represent the direction, okay? Because here the edges are ordered pair, the order matters, okay? So we also have AD going from A to D, going from B to C, B to E, E to A, E to D, F to E, D to B. And note that interestingly, between C and E, we both have edges going from E to C and also have an edge from C to E, okay? So this is what you see here shows the same information as this graph, okay? Now, why do we want to put a direction on the graph? Well, this is usually, in many cases, naturally, the relation may not be symmetric, okay? So, oops. Okay, and yeah, there's information flow naturally going from A to B, and you want to use this ordered pair to represent that direction. Okay, so why is the information not symmetric? Say you're on Twitter, okay, and then let's say we have a network representing who is following who on the Twitter. Okay, so every node would represent a person, and then an edge would represent that a directed edge A to B means that A is following B. Okay, and clearly on Twitter, someone may be following Elon Musk, but Elon Musk may not follow them back. So then you have only an edge from the person to Elon Musk, but not the opposite direction edge. So such a relation is not symmetric. Okay, and there can also be, for example, in the brain network, you have different neurons, okay? And then the neuron interact with each other, but the information has a specific direction. The information can flow from neuron A to neuron B, but not the other way around. So then you also want to have a directed edge, an ordered pair going from A to B, okay? All right, note that in a directed graph, we typically allow to have self-loop, namely you could have, say, we could have a graph A to B, but then A could have an edge back to itself. Okay, so this is allowed, a self-loop. However, in this class, we're going to consider the so-called simple graph. Okay, what that means is that for any two ordered pairs, say A and B, there can be at most one edge. Okay, it cannot be that we have multiple edges from the same pair. That cannot happen. Okay, so this cannot happen. However, note that between A and B, because edges are directed, so A to B is different from B to A. So this is fine. Okay, so this is okay because A to B is different from B to A, okay? But between the same ordered pair, say from A to B, you cannot have more than one edge. So that's called simple graph. And in this class, in what follows, we'll always assume that we have simple graph, all right? Okay, now, so that's directed graph, okay? So what is undirected graph? Well, as the name suggests, here, we're going to remove the direction from the edges, okay? In particular, undirected graph is a pair of a set graph nodes, okay, and a set of edges where the edges is just a set of unordered pair, okay. So for example, here's one example where the nodes are A, B, C, D, E, F again, and the edges are now, all of this are undirected. And again, visually, it's much more convenient to plot them as real nodes, and from the edge, I connect between the two nodes, okay? So for example, here we have an edge AB, there's no direction. I could have also written this as BA. This would be the same, okay? And we have AD, AE, which is same as EA, and so on. And note that between CE now, I have only one edge can only have one edge between them. Okay, in the previous direct example, we had two edges in two different directions. Okay, so it's very similar to the direct graph. The only thing that you have a bunch of nodes, and then between each pair of nodes, a pair of nodes can form an edge, and then the edge AB will be the same as the edge BA. Okay, all right. Now, really, an edge is just a subset of nodes with cardinality 2, namely a pair of nodes. Okay, so the right way for us to write is actually it's a set of 2 nodes. So we really should use the notation of set here. Okay, so because there's no order. Okay, however, by convention, we still write it as just like before. We still write using the parentheses here, A, B. Okay. Well, now whenever you see this in the edge for directed graph, this means that an edge going from A to B, there's a direction. But for undirected graph, this is really just means the 2 nodes A, B. Okay. What this means is that since there's no order, A, B equal to B, A. Okay. Because really this is just a set of 2 nodes. Again, we consider in this class only simple graphs. That means that there's no self loops of the form. That means that between any 2 nodes, there's at most 1 edge, okay, A and B. So there's at most 1 edge. And so this is good, but this is not right. This is not a simple graph. You cannot have multiple edges between the same pair of nodes. Okay. Now, different from the directed graph, now we also typically do not allow to have self loops A to A. Okay. So that's the small difference between directed and undirected graph. Okay, and there are many cases where we do not necessarily need a direction between the nodes. That's why where the undirected graph is used for. For example, most of the time in the road network, most of the time between 2 nodes, you just have a road, you can go either direction. It's both, most of the time it's 2-way, okay? Of course, sometimes you have one-way street, in which case then it's more natural to model that using a directed edge, okay? And in the chemical network, it's usually what happens is that 2 compounds can interact with each other. There's no direction. It's just that these 2 compounds come see each other, then they start to interact. So usually there's also no direction there. Okay, so both directed graph and undirected graph are very common in practice. And when we model our data, we should decide what is the best, the most suitable way to model that, whether we should use directed edges or undirected edges. Okay, so again, that all depends on whether there is information flow or the relation should be asymmetric or not. Okay, so in one of your homework problem later for the coming week, you're going to just have some simple examples and ask you to decide, is it better to use directed or undirected network to model them? Okay, all right, but here's the summary of what we said. Graph is a very simple type of data. We're basically given a bunch of nodes and also edges, which is a pair of nodes to show some potential relation between them. Okay, and we talk about both directed graph and undirected graph. And here's a summary. Directed graph, the edges has direction, while undirected graph doesn't have direction. Okay, and typically in direct graph, we allow to have self loop, but usually not in the undirected one. This is just a convention. It's not essential. Okay, and now because of directed graph is ordered to pair this direction between 2 nodes, so then they could have opposite edges. A and B is not the same as B and A, while in the undirected graph, okay, A and B is the same as B and A. So there can only be at most 1 edge between a pair of nodes A, B. Okay. All right.